Hi everyone, and welcome to our video on net area. So net area is where we consider areas below the x-axis as negative. Or you can read this and consider the top of the regions above the x-axis and then subtracting the regions below the x-axis. All right, so let's show this. So the net area, so I would say a quick summary was what I first said. So this is just saying areas below x-axis are negative. Okay, so that's what net area is kind of going to break down to. Okay, so let's see this example here where we let f of x equal this absolute value, x minus 1, and then minus 1. We're going to use geometry to find the net area bounded by the graph of f and the x-axis on 0 to 3. Okay, so let's go ahead and sketch this out. And when you have net area, I'm going to box that. So it says just use geometry to find the net area. Okay, and with this sketch, okay, so we could plot it if needed. Let's go ahead and get our graph going. If you know how to graph this right away, that's awesome. You could also use a graphing or a table. But let's go ahead and since we can just go ahead and graph this real quick. Okay, so I've got the absolute value of x minus 1 and then minus 1. Okay, and then we can see it right there. Okay, so absolute value functions make that V shape. And it looks like it starts at 0, 0, and it goes down to 1, negative 1. And then we wanted to end at 3, so 3, 1. So let's make this sketch on this page. Okay, so we said it starts at 0, 0. And then it went down. And then it went back up, something like that. And let's label these points. Okay, so we started at 0, 0, and all I cared about, so because of this, 0 to 3, so 0, 0, when we plug 1 in, we got, so there's 1, negative 1, here's 2, 0, and then here would be 3 and comma 1. Okay, and we could verify that with a table too if needed, but this is it. All right, and so what we've got is this shape. And we're using geometry to find the net area bounded by the graph of f. So that's our graph of f and the x-axis. Okay, so right here I'm going to do red like that. So this would be considered a negative area, and then the blue above the x-axis. So from 3, so it wants us to stop at 3, so that's why I'm doing that vertical line there to hit it back to the x-axis. This right here would be considered a positive area. Okay, so we have positive area, and this in the red is like a negative area. Okay, and so they want us to use geometry. Well, these are just triangles. So we could use Riemann sums like in our previous videos, but those take a very long time. So if we have a nice geometric shape, we could just use our formula for a triangle. Okay, so our area formula for a triangle, let's just put that up here. So area of a triangle, I'm going to do capital A is equal to, it's usually 1/2 base times height is what we think of it. And so on our first picture, we'd have, let's label it, I'm going to use green for our dimensions. Okay, so for this one, well, we can see it goes from 0 to 2 on our x-axis, so that's a length of 2, so that would be considered the base of this triangle. And then the height is the perpendicular distance, so that would be, I'm just going to do it nice soft dot right there to there. Okay, so that dotted line would be the height. And we can see, well, it goes from the 0 y-coordinate to a negative 1 coordinate, but we would still say the length is 1. So we've got the height here is 1. Okay, so for the negative area, so it's still negative, but I'm going to set it up. So our area would be 1/2 the base times 2 times the height of 1. And so we have this area does simplify to become just 1, but because it is negative, so all we have to do is just, so geometry formulas don't make things negative on their own. We just have to make sure we do it ourselves. So we're saying this area is -1 because it's below the x-axis. Okay, and then in the green, or in the blue, I mean, in the blue triangle, we have our positive area. So it is still 1/2 base times height. Well, the base on this one looks like it's 1. So from 2 to 3 is 1. And then the height is also 1. So from 0 to 1 is 1. So it's 1/2, 1 times 1. And then this all simplifies to be 1/2. Okay, so we're going to consider that positive, though, like this. Okay, because it's all above the x-axis. And then so for the net area, all we do is we're going to take those two and add them up now. The net area is 1/2 minus 1. Okay, so we're taking the positive one and subtracting this negative one. So 1/2 minus 1. So our net area is negative 1/2. Okay, so that's our net area. So the net area, all it's telling us, so the negative, so in geometric sense, it really doesn't make sense. We usually don't have negative areas if we're talking about something in an application. But what this really means is just we have more area below the x-axis than we do above. Okay, so that's all that means. That's all it is. So for if it was an application, maybe this is like a total distance traveled, and maybe this negative represents like we went backwards. Okay, so that's all it really does. Okay, so that's net area. Now in letter B, it says use geometry to find just the area. Okay, so area, so notice there's no word, the net is not in front of it. So area just means consider all of these regions as positive. Consider all regions as positive. Okay, well, we don't really need to do too much on this, so we have plenty of space. We have the same picture. Now, all we have to do, I might as well just sketch it. So if it's just area, so take just a second. Okay, and this is not to scale, but we're considering all these regions as positive. So this I am just going to put in 1 to say that's the area, and then over here was 1/2. That was the area, and then the area again, not net area. So careful with that one little word. Area is just make sure to just add them together. 1 plus 1/2, and that would be 3/2. Okay, so and this is more like a geometric sense where we are viewing it as we would if it was like a real life object, like the area of a floor or something like that. Okay, so that's the difference. So net area considers these anything below as negative. Regular area considers every region as positive. Okay, so that's how that breaks down. Let's see what else we have here. Okay, so we've got more geometry. Let's keep this going. So we've got a side note. All right, so on these problems, let me make a sketch. One more sketch. That's not super necessary. I just wanted it. On this problem, we could have done the Riemann sum with our rectangles. Okay, so, and we didn't really want to because geometry with the triangles was easier. Okay, but we could have done this. And what this is telling us, okay, so this was an option, just this sketch that with the rectangles, but again, we really don't want to do that. But this information, the general Riemann sum for f on some interval AB approximates the net area. So it approximates the net area. So Riemann sums are automatically doing net area. So if we have a function that goes below the x-axis, the Riemann sum, doing it the way that we've done before, would automatically account for it. Our general Riemann sum, so this notation we won't really use, but just to write it out, this is just still saying, so here is the height, however many there are, and then here's our base for each one. However, it's written in a different way than we did it in the videos. Okay, so the height's the same, or our base is always the same. The heights are different. Okay, anyway, what this is saying is if you use a Riemann sum, it does the net area. So Riemann sum does the net area, but we're going to add to it right away where we use what's called the definite integral. So the definite integral, let's put it right here. Let's put it right here up top. So the definite integral finds the exact value of the net area. Okay, so the Riemann sum only approximates it. So like what we did, let me scroll, but it's erased. Like in these videos, so we did the Riemann sum, and these were just approximating the area, and it was approximating the net area. Definite integral, what we're about to do, does the exact value, so it's more accurate. It's also faster, so it's a double bonus. Okay, and all this statement is saying here, if we were to do the definite integral, and the definite integral just means that you have little letters on the a and b here on the integral symbol, which means we'll start to plug them in very soon, equals this limit. So we haven't seen limits in a while, but if you do the limit as our base gets close to 0, that means we would have a bunch of rectangles. Let's go ahead and draw a picture. So what it's saying here, so if I have some function, okay, so here's, let's say, from A to B. So here's our area. So it's got some curve to it. That's okay. What this is saying, this net area, exact net area is equal to this integral that we'll do very soon. And it represents the limit. So what if I were to draw the same picture? So I'm going to just try my best. They're sort of the same. So there's A and there's B. What it's saying, what this portion is saying, is if you have an infinite number of rectangles. Okay, so mine, I'm not going to have infinite, obviously, but I'm just going to draw a bunch. So if you have an infinite number of rectangles, it would match this answer. Okay, so, and we can see my rectangles are definitely not infinite, but I just have it. Okay, so I'm just going to put more vertical lines. Okay, so if you have an infinite number of rectangles, the gaps that would have been from few rectangles are kind of getting filled in. So that way it does match up exactly. It fills in this exact area. There's no gaps. There's nothing that goes above the curve. It's perfect. Okay, so anyway, so this here is just saying it will be equal to this, and it's easy to do. Okay, but first, all we're going to do is use geometry to evaluate these definite integrals. All right, so we've got, in number 1, it says use geometry to evaluate the definite integrals. Here, I'm going to just sketch this graph. Okay, so 1/2 x plus 4. Let's go ahead and sketch it. Okay, so 1/2 x plus 4. If we want to, we could even use our calculator. Okay, so might as well, just to really verify. Okay, so here's our calculator. I don't need that one anymore. Let's do 1 divided by 2 x plus 4. Let's put y equals. Oop. Okay, hold on. I don't know where it's gone. Let's go ahead and delete it and try one more time. It didn't graph it. Okay, so something was weird there. 1 divided by 2x plus 4. There's the graph. Okay, so we've got this picture. Okay, so we're going to copy this down. Let me make it that way. Okay, so there's our picture, and all I want to do is, I'm just copying it, but I mean, we might not have needed it if you used, this is a line, so you could have said, oh, I could go up 4, 1, 2, 3, 4 for the y-intercept, and then we'll go up 1 and run 2 to get the rest. So up 1 over 2, and then from there, oop, kind of missed the dot. Let's go something like that. There we go. Not the best. It's hard to draw with the pen, but there we go. Okay, and then it says, well, start from 2. So here's 2. So just draw in a vertical line until it hits the x-axis, until it hits the graph, and then go to 8 right there, like that. Okay, so what we have here, so this, we could use geometry because it is a trapezoid, but it's probably easier to think, hey, how about we just draw that right there and make a right triangle, and we have a rectangle as well. Okay, so let's go ahead and plot these points too, where the graph hits these. Okay, so let's reference back our picture. Okay, so I want to just look at 2, and I want to look at 8. Okay, so there's those points, and then these I don't care about. Okay, so I have 2, 5 is one of the points, and I have 8, 8 is another. So let me label that on our picture. So we have 2, comma 5, and then 8, comma 8. Okay, so the reason for this is, well, again, if we're just using geometry, I'm going to do the area of a rectangle, and notice it's all above the x-axis, so it's all going to be positive here in this problem. But I'm going to use geometry to help us, so we know this here is 6. Okay, and then we can use this y-coordinate to help us know that this height of the rectangle is 5. And then we could also use this y-coordinate to help us figure out what this is. Okay, so, well, all the way is 8. But I don't want all the way. I only want that little segment. Well, 8 minus 5 would be 3. Okay, so that way we could start to break down our area. So we're to find this definite integral. So let's write it out. And then remember, this is just approximating, or not approximating. This is finding the exact value of the net area. So this is the net area, which on this problem is the area of a rectangle. Area of rectangle plus the area of that triangle. And then we'll just use our formulas. So the area of a rectangle is your base times your height. Well, it looks like it would be 6 times 5. Okay, so we have 6 times 5. And then plus the area of the triangle. Well, that's 1/2 base times height. Our base is 6. And our height is 3. Okay, so we've got those. Let me highlight these so that there's our 3 and 6 that are going right there and there. So that's our base and height. Okay, so now it's just order of operations. So this looks like it's 30. And then this looks like it's 9. Okay, so 1/2, 6 times, yep. And then add those together and we answered this question. So the definite integral finds this area, and I'm just writing it out just all to be with each other, is 39. Okay, so if it uses geometry, it's usually just rectangles or triangles. Now, on this one, we have a different scenario where we have this radical. Well, again, I'm just going to sketch it real quick. They use W, but I am going to change it to X. Okay, so we have square root of 4 minus x squared. And then you might recognize the shape at this point, and you might say, oh, that's just half of a circle. Okay, so we have half of a circle. Let's go ahead and sketch that. And I put the point so you can see those coordinates. It looks like it's 2. That's important on it. Okay, so let's sketch that. Okay, so if you ever have this, so as a side note, if it is y equals the square root of a squared minus x squared, this is just always half a circle, in case you wanted to jump straight to it. So it's a half circle with radius equal to a. Okay, so with our problem, let's go ahead and make that not the best sketch. Let's see if I can do it with my pen. Okay. That's okay for what we've got. Okay, so I have these points. So this was 0, 2. This was 2, 0. And this was negative 2, 0. And so the area that we're trying to find is all right here. And I didn't shade in the previous one. So we found, I'm going to use a highlighter. So we did find this area. That trapezoid area right there was what we found. Okay, anyway, so back to this. Well, a circle has a formula for area. So the area of a circle is equal to pi r squared. Okay, well, here it's a half circle. So let's make an adjustment. Half circle. Well, cut this in half. So it'd be pi r squared over 2. And then with our problem, it certainly looks like, well, our radius is right there. Our radius is 2, which again matches our formula in case we wanted to use it. So the square root of 4 is 2, so that's our radius, but we could definitely see it in our picture. And notice it did want it, so it's nice. They matched it up from negative 2, so it does start right there. and then 2, positive 2, which is right there. So it is the entire half circle. So if they change those values, we would probably have an issue. Okay, but with this, they usually set it up to make it nice. Okay, anyway, so our area then, let's set up our integral from -2 to 2 of 4 minus w squared dw. Again, all this represents, so once you see those little numbers on our integral symbol, just means you're finding an area, finding a net area. And again, it's all above the x-axis already, so it will be positive. And so we'll just use our area of a circle, half circle formula. It's pi times r squared. Well, r is 2, so 2 squared divided by 2. And then, well, this would all simplify. 2 squared is 4, divided by 2 is 2. It's 2 pi. And there we go. All right, we found it. Okay, so that's how you find these areas using geometry. Okay, so at this point, we probably won't be doing Riemann sums, all right, except for the ones that were in the homework or review for test or whatever. But so geometry and these integrals will kind of take over. Okay, so remember net area. If you have anything below the x-axis, net area counts as negative. Regular area counts everything as positive. Most cases are automatically above the x-axis, so we don't have to worry too much about it. Okay, but that's it. So there's our formulas that are important. So if it says use geometry, it's either your rectangle formula, triangle formula, or circle formula for the whole thing. Okay, so that's that. If you have any questions, please let me know. Otherwise, thanks for watching, and I'll see you again soon.